Okay, so empirical rule. Empirical rule is used whenever you have data that is both symmetric and unimodal. So maybe you've got a histogram and it looks something like this. Just to make up an example here. So this here it's unimodal. There's one peak, and it's pretty symmetric, pretty even on both sides. Not perfect, but it's approximately, it's roughly symmetrical. So whenever you've got data like this, what we can do is we can fit a model. We're going to fit a bell-shaped curve to our data and use that to approximate where does most of our data fall based on the average, x bar, or if we're thinking theoretically, we'll look at mu, and the standard deviation, which theoretically we write as lowercase sigma. So we need these two pieces of information, and we're going to fit this to what's called the normal curve. So you might see this the same scenario written as capital N for normal, and they'll tell you either the x bar in this standard deviation, or they may write it using the Greek letters mu and sigma. Both these things mean basically the same thing. So I've got a couple example problems here to look at. These were from the homework. So the first thing they tell us to do is we're going to sketch a curve for grade point averages at a university. They tell us that the GPAs fall under a normal curve with average 2.6 and standard deviation 0.4. And some of the questions they want to know is find the percentage of students who have GPAs between 1.8 and 3.4. Alright, so before I go any further, I want to talk more about what the normal curve is and what we do when we look at it. So, and what these numbers up here that I've written down mean. So whenever you've got roughly symmetric data, you can fit it to a bell curve. If it's symmetric, then the average should be somewhere in the middle. So there's our x bar, or you may see this written as mu. And then we look at standard deviations away from the average. So if we go, for example, one standard deviation above, that would be somewhere over here. So that's one standard deviation, or if we're thinking in Greek terms, we use lowercase sigma. We can also go in the negative direction, the same amount. So negative 1 standard deviation or negative 1 sigma. And if you're looking at just this part that falls within this range inside, that actually turns out to be 68% of our sample or of our population. So that's what the 68 there is for. So you might be able to figure out that if we go 2 standard deviations, then the amount of stuff under the curve in this section here would be 95%. And then if I go 3 standard deviations away, either above or below, that actually takes in 99.7% of my data. So what I want to do is I want to replace x bar with what the average actually is, and the standard deviation with what the standard deviation looks like to be. So what I want to do here to solve this problem is I want to make a bell-shaped curve, like so. My average occurs, according to this data, at 2.6. That's the GPAs of on average is 2.6. And if I go 1 standard deviation above, I'm going to add 0.4. So 1 standard deviation away would be a GPA of 3. If I add another one, it'd be 3.4. If I add another one after that, it'd be 3.8. And if I go in the opposite direction, 1 standard deviation below is 2.2. Another standard deviation would be 1.8. And a third would be 1.4. So I want to find the percentage of the study that was between 1.8 and 3.4. So what percentage of the population falls inside here? Well, we said just a second ago, this is -2 standard deviations and +2, and in that range would be 95% of the population. So 95% of our population falls between 1.8, a GPA of 1.8 and a GPA of 3.4. So that's pretty good. Part B asks for how much falls greater than 3.4. So here we have to think a little bit. We know that this part here inside, we just said that was 95%. And if you take the whole area under the curve, that would be 100%. So 100 minus this part we've shaded in would leave 5%. So we've got this part here plus this part here, that'd be 5%. But this is symmetric. So if I cut it in half, this right here is 2.5%, and this right here is 2.5%. So therefore, 2.5% of the population would fall in this section here that would be greater than 3.4. Alright? Part C wants to know less than a 3.0. So 3.0 would be right here. We said that this part in here was 1 standard deviation above and 1 standard deviation below, and altogether this was 68%. So what we need to do to figure out this one is we need to break these things down and split them apart a little bit. So let me erase this part where we shaded in. I'll redraw some lines like so. So if all together inside here is 68%, then 34% is right here, and 34% is right here. I'm just cutting things in half. So know that this is 68 altogether. Half of that would be 34 and 34. Alright? So I know that altogether this distance here would be 95% of my data. But I already know that this part in the middle is 68. So 95 minus 68 leaves 27% to be here and here. If I cut that in half, I get 13.5% and 13.5%. And then we said just a second ago in the last problem that this section here is 2.5% of the data. So it would make sense that from here over would also be 2.5%. So I don't know, what's the chance of being less than a 3.0? Well, altogether here, this is 68 plus 13.5 would be 81.5 plus 2.5 would be 84%. So 84% of the population is below a 3.0. So you're just adding up these percentages here. And the last question asks for bigger than or greater than a 1.4 GPA. So 1.4 is all the way down here. We said that this would be 3 standard deviations away. So this section here at 3 standard deviations is 99.7% of the population, which means that the part that's outside of that, this section here and this section over here, if you add those together, that should be the other 0.3% that we're missing. So if I cut that in half, then only 0.15% of the population is less than a 1.4, which means that 99.85% of the population is greater than a 1.4. Remember that all these things have to add up to 100 because 100% of our population is under the curve. So hopefully that was informative and helpful. I might post another video here in a second that talks about, instead of finding percentages, maybe they give you the percentage and you've got to find what the GPA would be, or it might be a different scenario. So stay tuned.